Okay, so we've spent a whole bunch of time talking about different function types. Something about linear functions. We've talked about absolute value and quadratics and polynomials and rational functions and roots and radicals and exponentials and logs and all kinds of stuff. And this last little bit of stuff, what we're going to look at is how we treat two or more functions together, talking about systems of equations, which is what we call that. So when we talk about a function like, I don't know, y equals 2x plus 1, that's relating a whole bunch of infinitely many, in fact, x and y values together, right, at the same time. And all the x values we call the domain, and all the y values we call the range. And then this function describes specific examples of those and how they go together, right? Y equals 2x plus 1, that's a straight line with y-intercept 1 and slope 2. Right, so for example, it goes through 0, 1, and then up 2 and over 1, 1, 3. And a whole bunch of other points in between and infinitely in both directions, right? So this on itself, by itself, again, describes a whole bunch of things. What we're going to be looking at is systems, meaning, take two or more of those things and join them together. This is the example that I did in the intro video for this week. I'm not going to work through that again because hopefully you watched it already, but we're going to take two of these things and consider them at the same time, right? So x plus 2y equals 5, that's a linear equation. If I graph that, it's a straight line. Again, it's a whole bunch of points all together with this specific relationship. This, same idea, 2x plus 3y equals 5. It's a straight line. It's a whole bunch of points that have that specific relationship all together. This big curly brace means what it always does. This stuff goes together, right? It's the same situation. It's the same x and the same y. So what we're looking for then are a point or any points, if any exist, where both of these things happen at the same time. This is called a 2x2 system because it's got two equations in two unknowns, right? I don't know what x is, I don't know what y is, but I've got two equations that relate them together. That's the 2x2 part. And everything here is linear. There aren't any exponents on anything, right? It's all x to the first, y to the first stuff. So this is a 2x2 linear system. That's what we're going to stick with for today. When we get back from break, we'll talk about nonlinear 2x2 systems. So what if there's a quadratic or something else in there, right? A square root, whatever. Nonlinear systems. And then we'll look at larger systems as well. General idea is that you can find as many things as you have equations for. So if I want x and y, two unknowns, I need two or more equations before I have a shot at being able to solve that. We'll look at 3x3 systems later, so you'll have an x and a y and a z. That means we need at least three equations telling me about how they relate to each other to have a shot at solving. Now, the graphical interpretation for what's going on is just that there's a line, right? That's the first equation there, x plus 2y equals 5. Again, infinitely many points that satisfy that. Here's some of them, right? Every point on that line solves that equation. Here's the other one, 2x plus 3y equals 5. Again, every point on that line satisfies that equation. What we want to do is consider them together. And when I look at them together, now things are different, right? How many points are there where both of those things are true? Just that one. That's the only point, and these are straight lines, right? So these are moving further apart this way, further apart, that way in the upper left. So there's just that one point where these cross. There's this one place where these things are true at the same time. And you can check. X is -5, y is 5. You plug into this, -5 plus 10, okay, that's 5. And -10 plus 15, that's 5 also, right? So that equation makes both of those statements true at the same time, and that's the only point where that happens. And if you think about taking two straight lines, that's pretty much the way things are going to go most of the time. If there's going to be, one place where they cross most of the time. So what we're going to work on today are the tools that we need to be able to solve a system like that. You got two different methods. They're called substitution and elimination, but the general idea is that to solve, that's not what I want. To solve a 2x2 system, we need to combine the two equations Now, what we want to happen is to combine them in such a way that we get rid of some information so that we end up with just one thing we don't know, because then we know how to solve that. We know how to solve equations with one unknown. The problem is that we've got two unknowns. So the general idea is that we combine these somehow, right? Put the two equations together so that we end up with just a single unknown, so that we have something that we're like more familiar with, better equipped to deal with. Okay. And we've kind of got two different ways that we can think about doing the combining part. So first of all, just kind of looking at these two equations, do you see anything? Does anything jump out at you? Six x minus y equals 5 and x minus y equals 0. Okay. Multiply this by 6. If we multiply that by 6, what happens? Okay. Has that gotten us anywhere? Has that gained us anything? I mean, the 6 came from trying to get these to match, right? Okay, now they match. What do you want to do with it? Okay. If we subtract that whole thing, right? Think about those two equations and just subtracting one from the other. When you do that, the only things that you're going to combine are the like terms, right? So 6x minus 6x. Well, what's 6x? Take away 6x. 0. X goes away. Okay. Negative y minus negative 6y. So negative 1 plus 6 then, right, would be 5y. And then 5 minus 0. Oh, hey, what do we have now? Something that's only got one thing we don't know, right? 5y equals 5. If 5y equals 5, what's y? 1. What we just did was eliminate x. The way we did it was to take the x terms we were given, 6x and x, manipulate them so that they line up better, right? So that they're the same kind of thing, and then combine the two equations. We scaled the second equation by 6 all the way across, right? We're not changing anything. That's why we multiply both sides. One side happens to be 0, so it doesn't change. But we multiply the whole thing all the way across. I got 6x minus 6x, and then we notice that, hey, if I take those and subtract, those cancel, right? Those go away. We eliminated x. By eliminating x, we got a thing that's only got y in it that we can solve then, right? Now, once we have y equals 1, we still need to figure out what x is. Go back here, sometime before we eliminated x, right? I need x and y to both still be involved. Go back here and look for a place to plug in y equals 1. So for example, yeah, we could use the second equation. You could use either one, right? Just replace y with 1. And that means that x is also 1. So our solution to this system, and solutions are points because they have an x and a y coordinate, right? These are places where these lines intersect. Our solution is the point 1, 1. That's how elimination goes. You combine the equations by adding or subtracting. If you need to, you can scale one or both of them to make that that addition or subtraction kind of work the way that we want it to, right? To get stuff to line up. But then add or subtract, combine like terms, with the goal again of getting rid of something, right? Does everybody have what they want from there? Okay, so notice that like if I just went into this without a plan maybe, and just said, well, you know what, I'm gonna add these together. Well, if I add them together, 6x plus x is 7x. Negative 1y minus, plus negative y, so minus y. I would get that. Well, okay, there's like another piece of information, but does that really help me? Like, does that get us anywhere closer to where we're trying to go? Not really, because it's still got an x and a y in it, right? So I kind of have to have a plan a little bit, because if I just start combining stuff, kind of at random, I might not get something that takes me anywhere, closer to where we want to go. Anybody see another way we could have done the elimination here? What could we do to eliminate y? Negative y and negative y. What if we just subtract them the way they are? They're the same, right? The y term in both equations is identical. If we subtract those, what happens? 6x minus x, so 5x. Negative 1y minus negative 1y, so that's going to be negative y plus y then, right? Which is 0. And then 5 minus 0. So we get x equals 1 first. Right? So you could also do an elimination like that. And then again, you would take your x value and plug it back in and figure out what y is. So that would also work. Now, at the moment, with linear systems, you can always do any problem using whatever method you want, right? There's not a right way and a wrong way. There's not stuff that works sometimes and stuff that doesn't work sometimes. That'll change a little bit when we get into the nonlinear stuff because of the way you combine things. But at the moment, we can do whatever we want on any given problem. So the thing I want us to kind of be, thinking about for today anyway, is looking for, like efficient ways to do things, right? What do we look for to figure out, hey, this might be a better place to try elimination, or this might be a better place to try something else, or here's the thing I want to eliminate rather than this, or whatever, right? But again, we get to the same place. Okay. Well, another option, so that's elimination, right? Combine the two equations, add or subtract them together, maybe scale one or both if you need to, but add or subtract to get something to go away, get something to drop out. Another option is to look for something you can solve for, right? And we call that substitution. The way substitution works is we choose something to solve for in one or the other equation. So I might look at this and say, hey, I see an x all by itself here. I'm going to solve for that. If x minus y is 0, what would you do to get x by itself? Add y to both sides, right? So x equals y then? Okay. Well, we've used information from this equation then, right? We've only used the bottom line. It told me that x and y have to be the same for this to be true. The way a substitution works is that you then take that and combine it with the other equation. That part's important. You have to tie the two things together at some point. So you take that and plug it into the other equation. So 6x minus y equals 5, but what we just learned is that wherever I see an x, I can write a y instead, right? Because they're the same. So wherever I see an x, I can write a y. And then again, we have a thing that's only got one unknown in it. It's in terms of y. And that tells me that y's got to be 1. And then again, once I've got one of the things, I just back up somewhere and plug it back in and find the other one. If y is 1, then, for example, the second equation says x minus 1 is 0, so that x is 1. And again, we get our solution, the 0.11. Now again, we decided to solve for this, so we could have chosen something else to go after, right? What I'm trying to do is pick something that is going to be, as direct as I can get for the amount of stuff I'm going to have to do to rearrange to get it by itself, right? So I see x minus y, I've got 6x minus y equals 5, or x minus y equals 0. This, of all those things, looks like the one to me that's going to be the easiest to isolate, right, to get by itself. If I'd chosen, 6x minus y equals 5, and said, hey, I want to solve for x here, you can still do it. It's just that it's a little more complicated, and that means I've got, that much more stuff to like deal with later on down the road, right? Doesn't make it wrong, just means it's going to take me a couple extra steps to get there probably. And it means that I'm doing a little more arithmetic, right? If you look at what's happening in a lot of these, we're doing a bunch of little like multiply and add and that kind of stuff. And every additional one of those is another place that you could just, goof up and make a little mistake that, throws the thing off then, right? Because of course, if you make a goofy little arithmetic mistake here, this is going to be wrong. That means that's going to be wrong, right? And that's frustrating, even if you have like the right idea for how things are going. You end up with the wrong answer. Okay, so that's what substitution looks like. Okay, do you have any questions about anything so far? Okay, cool. All right, well, take a look at this and, I don't know, think about what we might be able to do here. Again, no wrong answers. There might be things that are going to be a little more straightforward than other things, but that's all at this point. What do you see? What do you want to try? Substitution, you pick something to solve for. Elimination, you pick something to get rid of.
Elimination.
Okay, what do you want to eliminate? Okay. You'll notice that I'm being, kind of particular, like I'm writing out what I'm doing and kind of leaving notes and trying to keep things organized. Where we're going next week, we're going to do this with nonlinear stuff. So the equations themselves are a little more complicated because there might be a square in there or something. After that, we'll talk about 3x3s. So we'll have 3 equations and 3 unknowns, which just means we've got more stuff to keep up with. Keeping in mind what you're trying to do, I think becomes an important skill then, because it's easy to sometimes get lost and kind of lose the forest for the trees. So that's kind of why I'm doing that. So if we're going to try to eliminate x, I don't really care about what's going on with any of this other stuff for the moment. I just want these to match, right, so that I can eliminate. I've got 1x in the first equation. I've got 2 x's in the second equation. What do we need to do to get those to line up then? Multiply that by 2. Okay, so I'm going to multiply that whole equation all the way across by 2. That's 2x plus 4y equals -2. The other one, the coefficient on x is already 2, so I'm leaving it alone. I'm just copying it over. Because again, the thing I'm trying to do is eliminate x. Now the coefficients match. We've got 2x and 2x. Right? We scaled the first equation by 2, left the second one alone, but we've got 2x and 2x. If we want to eliminate x, then what do? Subtract. They're the same, so if I subtract them, they go away. Right? 2x minus 2x is 0. But then we also subtract the rest of the way across. 4y minus y is 3y, and negative 2 minus 4 is negative 6. And again, just be really careful with all the little arithmetic stuff, right? We're not going to be doing any like difficult, scare quotes math right now, but we are going to be doing lots of little math things, right? And again, any one of them, a little mistake throws kind of the whole thing off, right? Which is annoying. But so if 3y is negative 6, then y is negative 2. Okay, now what? Plug it back in somewhere, right? Wherever you want. If any place looks more straightforward than any other, go with that. It doesn't really matter though. So take this, plug it back in somewhere. That's called back substitution. Basically, like you back up and substitute. So if you see that anywhere. If y is negative 2, then, for example, that first equation becomes x plus 2 times negative 2. So x minus 4. And then add 4 to both sides, you get 3. The solution to the system then is the point, the ordered pair, 3, negative 2. Okay? Yeah, did we feel all right about that? Okay. This is one of those things that like you kind of have to work through it, a few times on your own. I would encourage you, again, at the moment with the linear stuff, you can always do either, right? You can eliminate x, you can eliminate y here, and it would go pretty much the same way, right? You multiply this one by 2 instead, but then you do pretty much the same thing. You can always do either with linear stuff, with nonlinear stuff. Sometimes we have to be a little bit more particular. You can also substitute here, right? If I was going to do a substitution, I would probably want to pick either this or this to solve for, because then at least I don't have to divide, right? Like if I solve this for x, I got to move stuff around, and then I also have to divide the whole thing by 2. And I end up with, something kind of like this that I then have to manage, and just makes the arithmetic a little messier, right? So I would probably choose one of these two things if I'm going to do a substitution rather than one of these. But again, you can do it either way and it'll still work. It's just a question of, how messy the stuff in the middle is going to get maybe. So why don't you all take a minute and think about how you might go after this one. Okay, what do you think?
Times divided by 2.
Okay, why?
To get everything from the x's to be 4 and 4.
Okay, so if I look at, well, first of all, the first thing I would look at here is coefficients on everything, right? 4 and 3 and 2 and 5. I'm just gonna like write substitution off then, probably, right? And just say like I'm not even gonna get into that. Let's look for a way to eliminate things. If I start looking at elimination, then I'm comparing the like terms, right? So I've got 4x and 2x. Okay, what if 4 and 2 both go into? Like least common multiple for those. 4, right? Okay. So 4, well, one of them's already 4, the other one's 2. So I can do that by multiplying this equation by 2, I'll get those to line up. If I look at the y terms, 3 and 5, least common multiple for 3 and 5 is 15. So I would need to multiply both equations then. 15's bigger, right? So the numbers are going to be a little bit bigger. I have to manipulate both of them. That means there are 1, 2, 3 more opportunities that I could, do some silly little arithmetic thing that like throws the rest of it off, right? So if I'm thinking like efficiency, eliminating x there feels like probably the way to go then, right? Doesn't make any of the other options wrong, but that feels like it's going to be the thing that's kind of the most painless, right? Like quickest to do would be eliminating x there. That's kind of where we're at right now in terms of like the decisions that we're making, how we're doing things. Doesn't make other stuff wrong. Okay, so to eliminate x, I would multiply this by 2, which makes it 4x plus 10y and 6. And then again, the other one I'm just going to copy over. So I have them like lined up. 4x and 4x, I'm trying to eliminate x, so we need to subtract. Okay, and 4x minus 4x is 0, and that's good because that's like what the plan has been all along, right? We've been trying to do that. 3y minus 10y would be negative 7, and negative 1 minus 6 would be also negative 7, right? Probably worth it, there to like pause, right? Go slowly, grab a calculator if you need to. That's fine, right? It's better to be sure here than to, go quick and get it wrong because of that. So y is 1 then. And then we need to find the x that goes with it, plug it back in somewhere, right? And looking at our options here, really none of them is any better than any other. So just plug it back in somewhere. If y is 1, then 4x plus 3 times 1 is negative 1. And that's 4x plus 3 then, right? So 4x equals negative 4, so x is negative 1. And our solution is the point negative 1, 1. Right? That's where those things intersect. Okay? Yeah. Everybody feel like you're kind of getting the feel for this? Yeah? Okay. Good. I mean, that's pretty much it. Like that's the main tool that we're going to need for the next couple of weeks or next week. Well, today and into next week for this last little bit of material is basically those two things, right? Substitution or elimination. So let's take a look real quick at, I'm going to leave these C, E, and F for y'all to practice with. Try something, then, if you want to check once you get an answer, just type these into Desmos and see if that's where they intersect, right? You do it with the calculator also, but you have to do some setup there. So you can, those sort of check themselves. My solutions aren't quite done, so they're not at Blackboard yet, but I'm working on it. Let's take a look at this one. Now keep in mind what we're talking about are intersections of straight lines, right? So 3x plus 2y equals 5 and 6x plus 4y equals 8. What do you think?
too, but you also get rid of
Okay.
y as well.
Okay. Yeah, so we might kind of see it coming, right? But let's, go into it like I'm going to eliminate x here. I'd multiply this by 2 to get the coefficients to match, right? We have 3. We're trying to match 6, so multiply by 2. So 6x plus 4y equals 10. And then when I copy the other equation over, 6x plus 4y equals 8. If I didn't kind of see something coming before, now maybe things start to, fall into place a little bit. If we're trying to eliminate x and we subtract here, what happens? 6x minus 6x is 0. But 4y minus 4y is also 0. So we get 0 on the left-hand side. On the right, 10 minus 8 is 2. So we get 0 equals 2, which is not true, right? We get a thing that is just a logical fallacy. Like there's no x, there's no y. This is just not true. Okay, so I think, well, maybe I goofed something up somewhere, right? Go back and check. Times 2 would be 6, and plus 4, and 10. Okay, not there. Subtracting, no, that's 0, that's 0. 10 minus, no, that's 2. Okay, I didn't make a mistake anywhere. This just says 0 equals 2. What's happening here? We're talking about straight lines, right? And solutions are places where they intersect, right? Well, looking at these lines, where you're maybe not as familiar with looking at lines in standard form, which is what these are, but the coefficients on x and on y, sometimes those are called direction numbers. They're the same, 6x, 6x, 4y, 4y. They were the same here too. We just scaled it up to see it, right? What that means is that those lines are moving in the same way. Only they have different intercepts. Lines that are moving in the same way but have different intercepts are parallel. And solutions are places where the lines intersect, but if they're parallel, then they don't, right? So the way this shows up in the, math is like this, that we get this thing that's, not true. But what that means is that these lines are parallel. Of course, you can graph them and see it that way too, right? Those lines are parallel. And parallel lines mean the system has no solution, because solutions are intersections. You probably won't need this terminology or anything, but the lines are parallel, like when they move in the same direction like that, they're called linearly dependent because they depend on one another. You could turn one into the other one by moving it around, basically. And the system, because it has no solutions, is called inconsistent because there's no way to make both of those things true at the same time. Okay. Well, we should probably expect something weird to happen in B also then. Talking about straight lines, like think about taking, two pieces of uncooked spaghetti and just dropping them on a table, right? Almost always they're going to intersect somewhere if you, extend it far enough, unless they're parallel. Or what happens here if we try to solve this? Think about how you can do that here. What do you see?
Times 2 on the top and then subtract the top.
Okay. Multiply that by 2. 2x minus 4y equals 8. And then the other, the other one is negative 2x plus 4y equals negative 8. Well, again, we can probably kind of see, something's happening here, right? Because what do you notice about all those? they're all the same, but with opposite signs, right? And if we add these together, because they've got opposite signs, right? 2x plus negative 2x would be 0. Negative 4y plus 4y would also be 0. 8 plus negative 8 would also be 0. We get 0 equals 0. Which is true, right? But not what I expected, and not, at face value. Actually, I'm going to need those again. Not at face value all that helpful necessarily, right? This is called a tautology, a statement that's just true, all the time. Well, what's happening here, if we think about the lines, the direction numbers are the same, the y-intercepts are the same, they're just kind of dressed up differently, right? They've got opposite signs. They're kind of disguised a little bit. Right? And that's what's going on here as well. That means these are not just parallel, they're going in the same direction, but also live in the same place. It's really two copies of the same line, only I can't tell that just by looking at it, at face value, right? But if I rearrange these, if I solve both of these for y, for example, right, they would be identical. They have the same slope and same y-intercept. It's the same line twice. If it's the same line twice, and every point on the line is a solution, then how many solutions do we get? Well, here's one, and here's another one, and here's another one, and every point along that line is a solution to the system then, right? So this is two copies of the same line. So again, they're linearly dependent because it's the same line. But now instead of getting no solution, we get a place where we've got infinitely many solutions. Anybody watching the recording back later, I apologize if you can hear my stomach growling in the recording. We pushed it a little too far for our mid-morning snack. All right, this has infinitely many solutions, but it doesn't mean just anything works, right? So it's two copies of the same line, but only points on that line are solutions, right? So if that line looks like this point over here isn't a solution to the system because it's not on the line, right? So what we can do is take one of these, right? Let me get some of this stuff out of the way a little bit. Take one of these and say I look at this and go, hey, I could solve that for x pretty easily, right? If x minus 2y is 4, then x is 4 plus 2y, right? So there are infinitely many solutions, and because these are lines, x and y independently can be any real number, right? Like there's a solution where x is 1 or where x is negative 300 or whatever. There's a solution where y is 5 or whatever. But once you choose one of them, the other one is determined, right, in order to sit on that line. So solutions all look like, for example, that. So that if I say, hey, I want a point on this line, you can pick your favorite y value, right? Like, I want y to be 7. Okay, well, if y is 7, then the x that goes with it needs to be 14 plus 18, right? So 18 comma 7 is a point on that line. But once I choose one of the things, the other one is kind of fixed, right, to actually land on the line. Basically, what we're doing is just thinking of this as a function, right? I just solved it for x in terms of y because that looked like the easiest place to pick something to solve for, right? Like that's all. I just want some way that kind of gives me a like formula. This is called parameterizing. It gives me like a formula for points on the line, right? So pick something that I can solve for, and then if I know one thing, I can find the other one. Does that make sense? So like, 0, 0 wouldn't be on this line because 0, 0 doesn't fit into that equation and make it true. But if you give me a y value, I can find one that goes with it. If y is 0, then x needs to be 4, actually, right? That fits the equation, that lands on the line, that solves the system. Okay? Okay, cool. So that's the idea, substitution and elimination. Again, for right now, you can use either one whenever you want. It's just that sometimes one might be a little, more fun than the other. Or one might be a little more exciting maybe. But these other examples that we didn't get to, at some point, I mean, take a break, right? Let the break be a break, but Sunday or something maybe, sit down and try a few more of these and kind of warm back up a little bit. And then next week, when we get back, we'll talk about using this in the case of nonlinear stuff. Okay? I hope you all have